now we have a last one. So just one comment, the video is a bit long, so there won't be live question, but you can ask directly on the chat. So learning to sparsify the TSP problem instances from James Fitzpatrick, Deepak, Ajwani, and Paula, Carroll.
Hello, my name is James Fitzpatrick. I'm in second year of my PhD in University College Dublin. I'm supervised by Dr. Paula, Carroll, and Dr. Deepak Ajwani. And I'm going to give you a quick overview of the work I've been doing in relation to learning to sparsify traveling salesman problem instances. So I'm sure everybody's pretty much familiar with this, but just as a quick recap, the traveling salesman problem is a problem in which we're given a graph built up of some vertices and some edges, and to each edge we associate some cost or weight. And what we want to do with this graph is find in it a tour of least weight. What that means is we want to visit each vertex exactly once on a walk through that graph. So starting at some vertex, we walk through each individual vertex. And the extra condition we have in that is that we walk through the graph in such a way that we start and finish at the same vertex, visiting each vertex exactly once. Now, the problem with this particular optimization problem is that the solution space is exponential in n, the number of vertices or nodes in the graph. The solution space is highly non-convex, so it's a difficult solution space to traverse. And worst of all, the problem itself is an NP-hard optimization problem. So the question is, traditionally, how do we solve problems like this and get to a solution like we have here on the right-hand side? So one of the most common ways of doing that is forming the TSP as an integer program. And one of the most popular ways of doing that is to formulate this problem as an optimization problem where we have associated to each edge in the graph, and this graph is a complete graph, a binary variable. And if we have a method for obtaining a solution for this particular formulation, what we'll get if we have a solution vector is if the binary variable in the solution vector takes the value 1, then the associated edge is said to belong to an optimal solution, presuming that the solution method we have gives us an exact optimal solution. And if it takes a value of 0, that means the particular edge does not belong to an optimal solution. So then the question is, do we actually have effective methods for solving such formulations? And the answer is, for the most part, yes. So we have the Concord TSP solver, which is probably one of the best cases of a success story in terms of integer programming and combinatorial optimization, which can effectively solve quite large problems, quite large TSP problems. If we think of this problem, though, slightly differently, we can think of it as, in a sense, a classification problem. So when we find the optimal solution, what we do is we find a set of edges that belong to the optimal solution or to an optimal solution, and a set of edges that don't. So in this sense, we can think of it as a positive class and a negative class. The positive class being the edges that belong to the optimal solution or an optimal solution, and the negative class being edges that do not belong to an optimal solution or do not belong to this particular optimal solution. Now, if we frame this as a classification problem from the machine learning perspective, we can think about this as classifying the edges, again, as in tour or not in tour. But we have to be very careful if we do such a classification, because we have to make sure that not only do we select edges that belong to an optimal solution, but they make sense together as an optimal solution. And that can be a very difficult thing to do. So for this work, we restrict ourselves to a slightly less difficult problem, which is to ask ourselves, can we select the edges, or can we identify edges which are very unlikely to belong to an optimal solution? And so doing, build some kind of hyperplane and some feature space that will separate the most of the non-optimal edges from optimal edges. And what we'll do then is remove them from consideration and then solve a reduced problem using traditional integer programming techniques. So just to give a clear idea of what I mean by this, traditionally when we try to solve an optimization problem like this, we have to traverse some kind of solution space. And what this image tries to represent is a set of solutions where each dot here is a solution. A red color indicates that it's a bad solution, and a blue color indicates that it's a better solution. So an exact optimal solution would be the one that is the best solution of this solution space. And if we have an exact technique for solving an optimization problem, we can typically find that, which is the solution here highlighted by the dotted line. Heuristics, on the other hand, will find for us solutions that are probably going to be good or hopefully near optimal, not necessarily. But the approach we take, again, is slightly different from either of these, where we try to remove as possible, or remove as many as possible, of the non-optimal solutions or the bad solutions from the solution space from consideration. And in so doing, consider a very, very much smaller portion of the solution space to find a solution that we're looking for. And hopefully when we do this, we don't remove the optimal solution from the set that we do consider. So from the perspective of the TSP, what this looks like is looking at a graph, and I'm going to pretend that this graph underlying the TSP is a complete graph. We're going to remove as many edges as possible from this graph and produce a much, much smaller graph H. And from this graph H, we're going to look for the edges that form an optimal tour in this graph. And hopefully the edges that form an optimal tour in H form the same optimal tour that they would in G, giving us coinciding optimal tours. But that might not necessarily be the case. So in order to do classification, we have to represent each of our edges with some kind of features. And building on a previous work, which takes the same approach towards reducing the traveling salesman problem, we first build some simple, relatively easy to compute features, which are based on effectively just comparing the weights of the given edges. So we take, for example, this edge that goes between vertex A and vertex B, and we look at its edge weight. And what we might do is compare it to the edge weights of those edges, those edges in the neighboring region. So for example, we compare the edge weight of the edge AB to the edges of those incident with the vertex B to give us an idea of how that looks in tandem with the edges in the neighboring region around B. And we might do that for A as well. So we compare the edge weight of AB with the edge weights of all the edges incident with vertex A. And give us maybe a slightly more global picture. What we might do is look at this edge weight and compare it with, for example, maybe the global maximum edge weight of the graph or the global minimum edge weight. And perhaps if this problem was a convex one, what we would be able to do is just use these as sufficient features to help us do our classification and remove as many edges as possible. But it turns out that that's not the case, so we need to build slightly more expressive features. So one thing that we do, inspired by some of the approximation algorithms that exist for the traveling salesman problem, or at least for the symmetric traveling salesman problem, is building features from minimum spanning trees. So again, we're going to pretend that this graph here is a complete graph representing the typical TSP problem. What we do is we want to find the minimum weight spanning trees for this graph. And if we find them and look at the edges, we hope that the edges that belong to these minimum weight spanning trees give us some indication of how important they are. So the approach we have to completing these features is to take the graph, our original complete graph that we have on the left, build a new graph which has the same vertices as the previous original graph, but none of the edges. We compute the minimum weight spanning tree in our original graph. We take each of the edges from those minimum weight spanning tree, or from that minimum weight spanning tree, transfer them into our new graph, and remove them from our original graph. We then compute another minimum weight spanning tree and repeat the same process by taking those edges, removing them from the original graph, and moving them into our new graph. We continue this a number of times, subject to some kind of computational budget. So maybe we have a number of rounds of minimum weight spanning tree computations, something bounded, for example, by the logarithm of the number of edges or the logarithm of the number of nodes in the graph. And what we do is we hope that by inserting these edges into our new graph, we can compute features based on the order in which they were inserted into that graph that tell us something about how important those particular edges are and how likely they are to belong to some optimal solution. Another set of features we build are based on the idea of exploring the LP relaxation of our integer programming problem. So at the beginning of this talk, I talked about formulating this TSP as an integer program where we associate binary variables to each edge. And effectively, this comes down to the formulation that we use called the Dancing, Fulkus, and Johnson formulation. Now, this problem is obviously a very difficult one to solve, which is why we're doing this work. But what we can do is create a much, much easier problem to solve by reducing or removing the integrality constraints from our problem, or forming an LP relaxation of our optimization problem, and also removing the subtour elimination constraints. So this image here on the left is just a depiction of this kind of situation. We have an integer program with the integer solution, integer program problem, sorry, with the integer solution indicated by a purple X. And what we can do is relax the integrality constraints and remove them. We'll still have some constraints left, indicated here by the red lines. And in our TSP problem, these red constraints might be, for example, the degree constraints which are left over. And what we can do is just solve this resultant LP problem. And what we get is some kind of solution to the LP problem, which lies on the outside of, or on the exterior, on the edge of the feasible region, which is indicated here by a green dot. And hopefully this solution will give us some kind of indication of which edges are and are not good in terms of being likely to belong to an optimal solution. So the non-zeros in the solution should hopefully give us this kind of indication. Now this might be far away from our optimal solution or might be close. But in order to improve this kind of indication, what we can do is add cuts based on the structure of that solution. So we might look at the solution to our LPs and, for example, introduce something like a sub-2 elimination constraint. And hopefully, when we do that and resolve the problem, we'll get some kind of solution that looks even closer or gets even closer to our IP solution. And we can repeat this process, again, subject to some kind of computational budget until we get close enough to get a very good indication of which edges do and do not belong to this optimal solution. Now, we have to be careful because even though now we can compute these features for our classification process, we have to make sure that we, in the end, have a resultant feasible graph. So what we do now is we compute the features for each of our individual edges, and assuming that we have some classifier that can take those features and produce us a yes or a no, indicating yes, this should belong to the set of edges that we consider, or no, it should not. We have to make sure that we have the possibility to even compute a solution at the end. So consider that we have the same graph that we had at the beginning. Here we have, for example, a possible solution, a possible optimal solution for that graph. On the right-hand side, we might have another optimal solution. So in many cases, we have several optimal solutions for a given graph. And what we can do is just put them all together and look at what the optimal set of edges looks like for a graph. What we would want to do in an ideal case is have a classifier that reduces our graph to this kind of situation, where we've removed all the edges that don't belong to the optimal set and retain only edges that belong to the optimal set, or the set of edges that belong to optimal solutions. In many cases, we won't do as well as that. In some cases, we'll do as badly as this, where we have some of the optimal edges, yes, and some of the non-optimal edges, but even worse, we don't have a situation where our graph can actually produce a feasible solution. So try as hard as you might, we won't be able to get a feasible solution to our traveling salesman problem from this graph. And to identify whether or not a graph admits a Hamiltonian tour is itself an NP-car problem. So in order to achieve feasibility or to guarantee feasibility a little bit more easily, what we can do is instead take a tour that we know to exist in the original graph and insert it into our pruned graph or our sparsified graph. So for example, we can insert a tour that looks like this into our graph. This could have been obtained from any kind of heuristic or even a possible a random tour. Now, if we choose to use an approximation algorithm to get us this kind of tour, what we can do is we can provide bounds on the quality of our sparsification. So we can say that the sparsified instance will admit a solution no worse than some bound. And we can also do things like insert tours from very good heuristics, for example, using a Lin-Kernighan heuristic to ensure that the solutions that we do get in practice from these kind of prune instances are typically quite good. So in order to do this, to train a classification model like this, we need to have labeled data. And by that, I mean we need to have a set of problem instances where we can compute the optimal solutions, the set of all optimal solutions for them, or as many as possible within some tolerance, and use those optimal solutions to identify which edges do and do not belong to an optimal tour. So our ability to actually do that is limited to an extent by the size of the problems. So the larger the problem is, the more difficult they're going to be to solve. So what we do is we select a set of benchmark instances, and with those benchmark instances, we choose relatively small problems and a subset of those small problems to train on. So in practice, what we do is we use the Matilda TSP instances. This is a set of 100 vertex problems divided into 7 classes, and each of these classes has 190 problems in them each. Now, based on some observations from some previous works and some experiments we did, we choose only to train on the difficult problem instances in that set to have as our training set, and we evaluate them on a TSP lib problem instances. Now, these problem instances have completely different, in some cases, weight distributions. The underlying graphs do, and the size varies from very, very small graphs with 17 vertices to upwards, I think, of 85,000 vertices, but we restrict ourselves to graphs here with 4,432 vertices. And these are the graphs we use to evaluate the performance of the sparsifier. We train simple models as well to make sure that the inference times are quick. So this means we restrict ourselves to very, very simple models for classification, such as logistic regression models, or slightly more complicated models or complex models, such as support vector machines. So just to give an indication of what the performance looks like for these kind of classifiers, we have a plot here, which on the horizontal axis shows the pruning rate. So this is the number or the fraction of the edges that are removed from our graphs. And on the vertical axis, we have the optimality ratio. So this gives us an indication of how the optimal solution compares to the optimal solution in the original problem instance. So for the pruning rate, as value of 0.84 would indicate that we prune 84% of the edges away from the graph, leaving only 16% of the variables that were in the original problem in the pruned instance. And an optimality ratio of 1.04 means that in the pruned instance, the best case optimal solution that we could get is 4% worse than the original problem instance. So again, we have 7 problem classes here in varying difficulty. We trained only on the difficult problems. So in this case, the ones represented by the blue pluses and the purple stars. We can see that the performance is actually worse for those. So these ones are obviously more difficult to work on and more difficult to prune. So the performance tends to degrade more visibly for these particular problems. And we measure the success of the pruning by the pruning rate we can achieve, so the number of variables that we can remove, and the resultant effect that it has on the optimality ratio. So in 65% of cases, we can see that we get optimal solutions for these Matilda problem instances. For these problems as well, in 95% of cases, we get within 4% of the optimal solution. So having removed as many edges as possible, we obtain solutions in our pruned instances that are no more than 4% worse than the original problem instance. For the TSP limb problem instances, what we observe is that in 95% of cases, we can get within, in 92% of cases, we can get within, or we can get the optimal solutions for these problem instances. Now, for the Matilda problem instances, we can prune typically above 85% of the edges in all the cases if we have support vector machine as the classifier. And for the TSP problem instances, it's a little bit different. So because we have such a large variation in the size of the problems, we can get pruning rates as low as 50%, meaning that we only remove about half the edges. This is typical for problem instances that are smaller than the training set, which were 100 instances or 100 vertex problem instances. But for the much larger problems, which go into thousands of vertices, we can prune upwards of 95% of the vertices. One of the nice things that we can do as a result of inserting the tours in the post-processing step to ensure that the resultant graphs are feasible is that we can control the optimality ratio to some extent. We can do this by controlling the pruning rate. And basically what we do is we take the threshold for the classifier and alter it so that we are a bit more parsimonious, a little bit less parsimonious with the number of edges that we have in our pruned instance. What that means is that we can choose to retain more edges, and that sense have it more likely that we're going to have a lower optimality ratio. This will lead to slower problem solving times, but better optimality ratios. We can control this directly as well as if we want, by simply selecting the number of edges that we want to retain. And just in terms of the TSP problem instance, we have some kind of representation here of the performance. On the horizontal axis, we indicate the problem order or the number of vertices, the size of the problem instance. On the vertical axis, the pruning rate. So we can see that as the problem size grows along the horizontal axis, the pruning rate typically grows in tandem with that as well. And one of the nice things is that there doesn't seem to be a clear indication that the parameters that we have fall apart for the larger problem instances. That means that the methods we have for computing the features for the larger problem instances seem to hold. And on top of that, there doesn't seem to be much of a correlation between the problem size and the optimality ratio. And this is one of the nice things here, because in a lot of machine learning approaches for helping to solve optimization problems or combinatorial optimization problems, and in particular the TSP, we see that, especially with deep learning approaches, that the performance tends to fall apart as the problem size grows vastly differently from the problem sizes that were encountered in the training set. Of course, we'd like to test these in larger problems, but this will require further optimization of the code base. So that's just a quick overview of the results that we have so far. And thank you for listening. And thank you for the opportunity to speak. And if you have any questions, I'd like to take them. Thank you.
So thank you very much.